lesson is a continuation of what we looked at in the first part of 2.6. We just finished by making a chart that was a summary of transformations, different ways that graphs can change based on what's happening in the equation. So in the second part here, we're going to see how we can actually use transformations to make variations of graphs. And so we're going to start by looking at an equation. We're going to describe the transformation in words. We're going to identify what the parent function is and think about what that graph would look like based on the library of functions. And then we're going to sketch the new graph. So what we can see here is that there's an x and there's a squared on this quantity outside of the x. And so that's something good to identify right away, that this is going to be a new version of a parabola graph. So the parent function is y equals x squared. And we can see that there's two things happening here. So we're adding 4 inside the function, meaning it's inside the parentheses. And so that's going to cause our parabola to move to the left 4 spaces. And then we're also subtracting 2 on the outside, on the end of it. So that's going to move our parabola down 2 spaces. So the way to make the graph is to actually start by graphing the parent. We're going to graph y equals x squared from the library of functions. We know that the table of values told us it's -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. So again, I'm taking those points directly from what we did at the start of the previous lesson. Now, rather than connecting them, I'm actually going to change my color here so I can get this to stand out. I'm going to take each one of these points and move them to the left 4 spaces and down 2 spaces. When I'm dealing with parabolas, I like to start with this bottom point here. This is called the vertex. So I'm going to take that vertex and move it to the left 4 spaces and down 2. That's the new vertex. Then I like to go to this point here on the side, left 4, down 2. And then I'm going to get this little point on the other side, left 4, down 2. See how it kind of has that same basic shape there at the bottom? We just moved our points. And I'm going to keep going with that. Left 4, down 2. Left 4, down 2. And actually with the parabola, those 5 points there do a pretty good job of getting the shape. If you want to go ahead and do the last 2 points, you can. I'm going to stop there, though, to save a little bit of time, and I'm just going to go ahead and connect those new points with that solid line. Now, you can keep the original dots on there if you'd like, or you can go back and erase them, but we'll just say that our final answer is always the graph with the solid line. Sometimes what I have students do is actually leave the parent graph on there, but they do the parent with a dotted line, just to show that's where the parabola started before we applied the transformations. In this case, before it moved left 4 spaces and down 2 spaces. All right, the next one involves a square root symbol. So this parent function is y equals square root x. That's another function from our library. Here we can see that it's subtracting 3 inside the square root, so that is going to move it to the right 3 spaces. And then it's adding 1 on the outside, so that's going to move it also up 1 space. So from the library of functions, we know that some original points for y equals square root x are 0, 0, 1, 1, 4, 2, and 9, 3. Rather than connecting those, or you can connect them if you want with a dotted line, I'm going to go ahead and switch colors. And I'm going to think about moving each one of these points to the right 3 spaces and up 1. Right 3, up 1. Right 3 spaces, up 1. And this one, it's going to go a little bit off the graph, but I can assume it's right about there. And then with my new color, I'm going to go ahead and connect those with a solid line. And there's the new graph. All right, the next equation that we have involves the absolute value sign. So the original parent function this time is y equals the absolute value of x. We have 2 things going on here. So first of all, we've got a negative sign. It's out in front, and so that means that it's going to be reflected or flipped over the x-axis. We also see that it's adding 5 inside the function, so that's going to cause it to move to the left 5 spaces. Okay, so I'm going to go over here and I'm going to think about the library function. I'm going to just start plotting the points. This is the original absolute value of x. Now I'm going to do this transformation in a few steps. So there's the original dotted line. I'm going to go ahead and switch colors. First thing I'm going to do is flip it over the x-axis. So it's going to have that same point 0, 0, but the other points are just going to flip over. I'm going to connect that one with a dotted line because it's not my final answer yet. My final answer is going to be that, then shifted to the left 5 spaces. So this vertex point here is going to move over here to -5. And then we can go ahead and extend the points out. And with green here, I'm going to go ahead and connect. That's our final answer. So sometimes we can make these graphs just in one step. Sometimes it's a couple of steps, as you've seen here, to get all of the transformations represented. All right, in this next one, we see the square root symbol again. So this one has a parent function of y equals square root of x. Two things happening on this one as well. Now this time, because the negative is inside the function, meaning it's inside the square root bracket, this one is going to be reflected over the y-axis. And then it's subtracting 4 on the outside of the function, so it's going to move down 4 spaces. Okay, so again, I'm going to start with the original points for square root x, 0, 0, 1, 1, 4, 2, and 9, 3. Just going to do a dotted line there. I'm going to do this one in a couple steps as well. So I'm going to switch to a new color. I'm going to reflect it over the y-axis. So it's going to have the same anchor point there of 0, 0. But now these points just get flipped over. So I'm going to make that with a dotted line because we're not done yet. And then the final step, one more color change, I'm going to take that red line and move it down 4 spaces. So now the new anchor point is at -4. All of the other points also move down 4 spaces. And now we can actually connect this with a solid line, and that's our final graph. All right, so now we're going to take a short break from graphing, and we're just going to think about what's happening with the equations. So we have some descriptions. We're going to write the new equation based on the description. For all of these, the parent function is going to be the parabola, y equals x squared. So in the first one, we have a graph that is shifted 5 spaces to the left and 2 spaces up. So we're going to start with y equals. If it ever moves left, right, and it's a parabola, we need to have parentheses with the squared on the outside of the parentheses. We're going to start with an x, and if it moves 5 spaces to the left, that would be adding 5 inside those parentheses. And it's moving 2 spaces up, so that means that we're adding 2 at the end, adding 2 on the outside of the parentheses. The next one is vertically stretched by a factor of 3 and reflected over the x-axis. So we're going to start with y equals again. Reflected over the x-axis means that we're going to have a negative in front, and if it's vertically stretched by a factor of 3, that means there's also a 3 that's in front of the x squared. The last one is vertically compressed by a factor of 1/2 and shifted down 10 spaces. So we'll start with y equals. Vertically compressed by a factor of 1/2 just means that we have a 1/2 in front of our x squared. Down 10 spaces means that we're just subtracting 10 on the end. So we get 1/2 x squared minus 10. All right, the last thing I want to show you is a strategy for how you can graph functions that have a vertical stretch or shrink, which is just another name for compression or being vertically compressed. So that happens when the function has a value, we'll call it a, multiplied out in front. So to graph it, you're going to start by rewriting the table of x, y values of the parent function. We're going to multiply the y values in that table by a, which is whatever number was out in front, but we're going to keep the x values the same. Then we're going to finish by graphing the new x, y values. So let me show you an example of that. If we want to graph y equals 2x squared, the description of the transformation is that it is vertically stretched by a factor of 2. Okay, the parent function is y equals x squared. So over here, for the table of values, I'm going to start by just copying the values for the parent function. So when x is negative 2 squared is positive 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Now we're going to take these y values and we're going to multiply them by a. A is whatever number we have out in front of our function. So in this case it's a 2. So we're going to multiply those y values by 2. So we have 8, 2, 0, 2, 8. And this is going to give us a new set of ordered pairs. So we're going to keep the x values the same, but we're going to now be using the new y values. So we're actually going to be graphing these points, negative 2, 8, negative 1, 2, 0, 0 actually stays the same, 1, 2, and 2, 8. So let's see what that looks like on our graph. So we've got the point negative 2, 8, negative 1, 2, 0, 0, 1, 2, and 2, 8. So we'll go ahead and connect it, and that is our new graph if it is vertically stretched by a factor of 2. Now, by the way, if you want to visually see the change from the original, you could actually plot the points from the original y equals x squared, and it's just going to be kind of a subtle change here, but I'm doing that one in red. We can see that those original points are a little wider, so the vertical stretch makes it a little bit narrower. Now we're going to finish by just quickly graphing another function using transformations based on y equals 2x squared, because this one also is vertically stretched by a factor of 2. So all we're going to do is take that graph that we just did, and we're going to move it to the right one space, because we're subtracting 1 in the parentheses, and we're going to move it up 4 spaces. So these are the 5 points that I'm talking about from the previous graph that we're going to go ahead and move right 1 space and up 4. So I'm going to start with the vertex, right 1, up 4, and then the points on the side will look like this. So we have the point 0, 6, and 2, 6, and we might actually not have enough space for the others, so the point 2, 8 becomes the point 2, 12, so that's actually going to be, no, actually it becomes the point 3, 12, because it's moved to the right 1 space and up 4. So it's going to kind of look something like this, and the points on the other side would look like that. So if you do have a vertical stretch, or if it's vertically compressed, I recommend making this version first before you try doing any other movements, like moving it left or right or up or down. It just makes that process a little bit easier. So that's how we can describe transformation in words. We graphed based on the new equation using transformations, and we were also able to write the equation from the description.